Okay, everyone, we're now time for James Baldini to tell us about cave microclimates.
Thanks very much, Ian, and thanks for the invitation to speak today. It's great to be here. Okay, so many people kind of think of caves as being very static in terms of their climate. And in fact, of course, that's why our ancestors chose caves as their preferred dwelling places, because the environment is reasonably stable. But it's actually not perfectly static. There are some changes in the environment of caves, so-called microclimatic changes. And that's what I want to talk about today. So this image here on the first slide is the back entrance to Yok Balun cave in Belize, in southern Belize in Central America. So why do we care? Why do we care about cave microclimate? First is for exploration. So if you're going to run into bad air, it's nice to know in advance where it might be. So we want to know something about ventilation and how caves behave in terms of air movement and so forth. But increasingly, it's becoming appreciated that particularly cave air carbon dioxide, and this is something that I'll spend most of the talk focusing on, is carbon dioxide. That carbon dioxide is a major control on stalagmite growth rates, which of course feeds into us understanding stalagmite climate records better. And as I'm sure as you're all aware, and I'm sure you heard from Ian and others this weekend, stalagmites are rapidly becoming very important archives of past climate. So anything that helps us understand how they form and the meaning of the climate proxy record within the stalagmite can only be a good thing. So understanding the microenvironment also helps us understand how ventilation works at certain sites and how this might have been buried in the past, and I'll come back to this. And it also provides us information about carbon sources and sinks. And this is a reasonably new topic, and I'll talk about that last. But before we talk about any of that in great depth, I want to show what's possibly the most data-rich graph I've ever produced, straight out of my PhD thesis. So here we can see all of 9 data points over 4 years, which actually isn't great. But to be fair to this graph and to my PhD thesis, it's actually not too bad for the time. You had to measure cave air carbon dioxide using these so-called chemical pump devices. So this happens to be the Drager device that I used. And obviously, you had to be present in order to take the carbon dioxide measurement. And in my case, it was about a 4 or 5 hour drive from Dublin, where I was based, to Crag Cave, which is where these measurements were made. So you could only do that every so often. So records at the time were actually very low resolution, and this wasn't an anomalously low resolution. The measurements were also relatively imprecise. So this is basically how you read the carbon dioxide concentration using a color-changing compound within these vials. And it's not digital, right? So is it 400 parts per million, or is it 600 parts per million? Maybe if you left it in a little longer, it might be 800 parts per million. It's hard to know exactly. So the measurements were reasonably imprecise as well. So this is Crag Cave. This is 4 years at Crag Cave. But what's the seasonal cycle in carbon dioxide at the cave site? And it's very difficult to tell based on these data. You might get a little bit of a hint here maybe, but it's nothing definitive. It's not at all straightforward to work out something as basic as what the seasonal carbon dioxide cycle at this cave site might have been like. Were there any short-term excursions? And by short-term, I mean daily or maybe even hourly excursions in the carbon dioxide record over the 4 years. Based on these data, it's not just hard to tell, it's impossible to tell whether there are any short-term excursions. So obviously, we're looking for something a little bit higher resolution. Okay, let's see if this will work. Okay, so does climate vary in caves? Does the cave environment change? Most cavers will know that yes, it definitely does. So this is just a short video of a lava tube in the Mojave Desert. Being a desert, it's full of a lot of dust. And this provides a reasonably rare opportunity to actually visualize how the cave air is moving in and out and around the actual lava tube. And this is actually very small-scale air movement. This is just so-called Venturi effects as the wind moves over the entrance of the site. Larger-scale air movements, say during seasonal shifts, would be a lot larger scale than that. So it wasn't until the advent of infrared sensors and improved memory and battery life that we were able to actually come up with records that were a little bit more meaningful. So this is the probe that we tend to use. There's others around as well, but we've been using this for years and it works well. A Vaisala probe. And this is the carbon dioxide record, so here's PCO2, and this is just month from over 2004 and 2005. So this is September to February. And you can see there's a lot of structure there. The automated logging means that you can measure carbon dioxide as well as temperature. I'll talk less about temperature because it's slightly less interesting than carbon dioxide. It's still very interesting, though, but I will mention it. Hourly measurements and the highest resolution measurements we've made using these devices have been on the order of seconds. So you can measure, if you wanted to, carbon dioxide every 10 seconds. Why you might want to is a different story, but it can be useful in some cases. And obviously, you can't measure for as long. But this means that you can leave the logger in situ, and barring some sort of disaster, like electronic short or somebody nicking your logger, you should have a good record by the time you come back after a month or after a couple of months. If we superimpose the Drager data from 2002 to 2003 over the same interval of time as the 2004-2005 data set, you can really see the difference in the resolution of these two records. There's all sorts of wiggles and excursions in the higher resolution hourly record that are just invisible in the Drager data. It's a different year, but we can assume that the variability is probably going to be very similar between the two. So we decided to take this a step further, and we know that carbon dioxide in cave air is a control on stalagmite formation. Stalagmites form by the degassing of carbon dioxide in the cave, and if the cave carbon dioxide concentrations are high enough, it prevents the degassing of CO2 and the subsequent precipitation of calcite. So one of my undergraduate students at Durham built this contraption, which isn't much to look at, but is actually really cool, and a great job for an undergraduate to do this. It's basically a conductivity probe. So this is electrical conductivity. It measures how well water conducts electricity, basically. And this is connected to a data logger and a battery pack and a funnel, which was used to actually catch individual drips of water from a stalactite, which were then channeled straight into the conductivity probe, the conductivity measured, and then when the next drip came along this pipe, and then out that plastic tubing down to a drip logger here. So we can measure the drip rate of the stalactite as well as the electrical conductivity at the same time as we were measuring the carbon dioxide. So my favorite part of this bit of equipment is actually this green kitchen cutting board that was used as the backdrop to this more sophisticated equipment. And I didn't notice it at first until my student pointed it out to me, but it's quite cool. So we have a drip conductivity logger over there and a carbon dioxide logger over there, and they're completely independent of each other. And this is what the data look like. So the cave air PCO2 is the red, the drip water calcium is the black and white circles, and they basically vary in sync. And what this is telling us is that this concept of degassing and calcite precipitation actually works really well. It's actually pretty much spot on. So this drip, so when CO2 is high, the drip is hanging onto the stalactite and isn't degassing quite as much. And because it's not degassing quite as much, it's not depositing as much calcium carbonate, which means there's more calcium in the drip to reach the stalagmite, or in this case, the plastic funnel and conductivity logger, and you have more calcium in the drip. Conversely, when there's low CO2, you have more degassing on the stalactite, and it's essentially pirating calcium away from the stalagmite. So all things being equal, if you have higher CO2 concentrations, you probably would expect slightly less deposition in the cave just because there's just less thermodynamic drive to degas carbon dioxide into the cave system. So then what we did was we placed a calcite spar. So this is just a very optically pure bit of very flat calcite on top of a drip in Crag Cave. So all these data so far from Crag Cave in Southern Ireland. And then we left it in there for 151 days while we were monitoring all of the things like carbon dioxide, cave temperature, drip rate, those sorts of things. And you can see the difference. After 151 days, this calcite spar is no longer just pure Iceland spar, but it has a lot of secondary calcite, basically stalagmite. It's basically new stalagmite, just a few microns of it, but new stalagmite growing on top of this calcite. And what we can do is, I didn't put it on the screen because it's really ugly to look at, but there's various stalagmite growth rate equations that have been developed over the last 20 or 30 years. They're really quite complex. But if you know all these variables, you can feed them into the equation, and you can work out how much calcite actually should have been deposited on top of this Iceland spar. So we did that because we were measuring all of these things, and we end up with this blue rectangle here. And that's the predicted growth. Then we sectioned this Iceland spar in half, and this is the overgrowth. So that's the new stalagmite that was growing on top of the Iceland spar. And lo and behold, the predicted growth using these equations more or less matches the actual growth, which is good news. That means we understand how stalagmites grow, basically. And in terms of developing paleoclimate records, of course, that's pretty fundamental. Okay, so CO2 concentrations in other years. So this is a 2009-2010 data set, and this is 2004-2005. Both are from Crag Cave, so they're just shown against the same months. They both show broadly similar measurement values in different years. So not exactly the same. There's different excursions in each, but by and large, the values are similar. There's a equipment failure at the same time in both records. That's just bad luck. The month of September was cursed, but there's no reason why that should have happened other than just bad luck. So basically, it's high during the summer in all years, and it's lower during the winter. So if we look at the temperature in the cave and the temperature outside the cave, we can see why this is. So when the temperature outside the cave becomes lower than the temperature inside the cave, it basically becomes more dense, and it floods into Crag Cave, lowering the carbon dioxide concentration in the cave because outside air has a much lower CO2 content than cave air. So you can see this happening really clearly. Just about here is really when it gets going. This is just density here. So this is when the outside air becomes colder than the inside air, and this is pretty much when the CO2 enters into its, or the cave enters its winter ventilation regime. So the ventilation is basically driven by the air temperature difference between the outside of the cave and the inside of the cave. So this is a cool figure of seasonal temperature differences around the world. This was put together by Eric James from Texas. And basically what it shows is that at high latitude sites, say the center of North America, you have a really high seasonality difference in temperature. And at low latitude sites, you have very low seasonal temperature difference. And what this means is you could predict that cave sites at higher latitudes would ventilate more thoroughly than cave sites at low latitudes. And this partially explains why higher carbon dioxide concentrations can be found at low latitude sites rather than high latitude sites. There's just less ventilation that happens at these sites. It's a little bit more complex than that, but there can be some surprises as well. But this tends to be what we see. So tropical sites tend to ventilate daily. So they have daily cave breathing, basically. As the nighttime temperature drops, it's actually colder than the average cave temperature. So it floods in, and then as the temperature rises again, it breathes out. And they do this more or less daily, but it's not quite as complete as a complete seasonal emptying of the cave air. So what about spatially? How does carbon dioxide vary in different caves? So this is just a small cave. So this is in the Republic of Ireland, close to Waterford in the south. This is Ballina Cave. It's very small, about 95 meters of passage. It's underlain it's overlain by a forest. Even though it's small, though, it is divided up by these constrictions, one of which is very tight here at the back, into discrete chambers. So even though it is small, the ventilation may not be that pronounced as you get further back. There's roots sticking into the cave system in some places, so it's very shallow. There's probably less than 2 meters of overburden in most places. So what we did was we built a homemade breathing device that meant that we could breathe in Baldini Cave without actually exhaling carbon dioxide. Because obviously, if you're out to measure, if you're going to spend several hours in a cave mapping the carbon dioxide concentrations throughout that cave, you probably don't want to exhale, which is a problem if you're going to do this. So what we did was we basically created a breathing device for about 10 pounds that would allow us to breathe more or less normally in the cave. We couldn't speak to each other, so we also had to develop a series of codes and whatever. But in the end, we used these Vaisala loggers to create this spatial map of carbon dioxide concentrations in 3 dimensions within Baldini Cave. And a few highlights, as you get further into the back of the cave, not surprisingly, the CO2 gets higher. So the most elevated values are actually in a small pit in the back of the cave. The lowest values are in this entrance chamber. There's the main entrance. There is actually a little skylight here. So there's quite dynamic ventilation in the main entrance chamber. The air is just moving back to and fro all the time, probably. But what I find really interesting is the presence of what we've started calling a carbon dioxide front, basically. It's this really high gradient of CO2 in the cave. And that's just here. So if you imagine a logger placed somewhere like here, you probably end up with fairly static carbon dioxide measurements until this front moved over the logger, and then you have a really big excursion. And that could go some way to explaining some of the variability that we've seen in Crag Cave and other people have seen in other cave sites as well. So this CO2 front is just constantly moving back and forth throughout the cave. So I vowed to never use that carbon dioxide respirator device again. So some of my students were keen, so I let them use it and let them map a larger cave system. It is a very awkward device, but it does work. So they spent about a week in Skullska Cave in Yorkshire mapping the carbon dioxide concentration within the cave. The cave is about 1.5 kilometers long, so it's a lot longer than Baldini. And at the end of the week, they realized that the distribution of carbon dioxide is pretty much the same as in Baldini, where CO2 concentrations are higher further back you go. No great surprise there. CO2 concentrations are lowest along the main passageway. The absolute highest concentrations were in something called the right-hand passage, where there were uniformly very high CO2. And we ascribed that to the fact that the sediment there had a lot of organic material, so there's probably some in situ production just through microbial activity of carbon dioxide actually within that passage. But the general trend was the same as Baldini. Okay, so let's move on now to a tropical cave site. So this is the cave site that I had in my opening slide, Yok Balun cave in Belize, which is really a fascinating place. Archaeologically speaking, it's great, but I won't have time to talk about the archaeology. So this is the survey of the cave. Here's the main entrance. This photograph here is the main entrance. Yok Balun means jaguar paw in Maya. Because there's a jaguar paw in the entrance, so it's well named. The back entrance here is the one that was on the opening slide, and we'll see that again in a couple of slides. So there's only minor seasonal temperature differences. The main seasonality at the site is the rainfall, not in the temperature. So there's only a few degrees of seasonal temperature change. But we monitored it for about 3 years. Here's the location of the carbon dioxide logger. There's the red circles or temperature loggers that were scattered throughout the cave. There's a barometric pressure logger here, and there's similar instrumentation on top of the cave as well. So we had a weather station on top of the cave. So we can compare the meteorological parameters in the cave with what's going on outside of the cave, directly outside of the cave, because the local weather station wasn't very local and also wasn't very good. So it's better to use our own data if we could. So we monitored pretty well for about 3 years or so. So this is what just some of the results. So this is carbon dioxide here. This is the air density. This is radon, which basically behaves the same as carbon dioxide in terms. It's a good tracer for ventilation. And this is just rainfall at the local Maya village. And what we can see is, surprisingly, it actually ventilates quite a bit during the winter. So this is the moment where the cave air temperature is higher than the outside temperature. So the cold air outside of the cave, and I use the word cold loosely because it's 22 degrees, but that's as cold as it basically gets. So 22-degree air is colder than the air temperature inside the cave, and it floods into the cave and reduces the carbon dioxide concentrations in the cave to basically background atmospheric values, so about 400 parts per million CO2. The cave has two entrances. One entrance is higher up than the other entrance, so more than likely what's happening is the cold air is flooding from the upper entrance and flooding all the way through the cave and basically emptying out the old air from the old CO2-rich air from the cave. What's also interesting about this record is that by pure coincidence, it happened to coincide with a large earthquake, a 7.1 earthquake. So we had heard that it may have happened, and really, we didn't really know that much about it until we got to the site. And one of the passages that we normally use to access the equipment was blocked by breakdown. So we're like, oh, this is weird. What's going on? Strangely enough, though, it didn't affect any of the cave microenvironment. Didn't even flinch. Some of the loggers were knocked out of place. But in terms of the actual air circulation, didn't seem to make any difference to anything within the cave site. And a 7.4 magnitude earthquake is fairly big, so we're kind of surprised at that. Didn't even affect the hydrology, which I haven't shown here. But if you go further back in time, maybe there's indications that it might have earthquakes may have affected the ventilation. So this is the back entrance again. So this is one of my PhD students, Isa Valshak, in the entrance. So several stalagmites have been obtained from Yok Balun cave for the purposes of reconstructing paleoclimate, but none of them are older than about 50,000 years, which is weird. And we've dated the back entrance is a collapse feature. If you go about 100 meters further back into the rainforest that way, you can find another cave, which is only about 50 meters long or so, but it's obviously an extension of Yok Balun, and it was just separated from the main cave by this collapse feature. But we looked at some stalagmites that were growing on some of these breakdown blocks, and we took a basal uranium series date from these stalagmites, and lo and behold, they date to 50,000 years. So this collapse probably happened about 50,000 years ago. And did it change the ventilation regime? Did it open the second entrance that lowered the carbon dioxide in the cave, which then allowed the rest of the stalagmites to grow? Maybe, but we don't really know for sure. But what's interesting to think about is that this highlights the importance, as we've heard in the last two talks, of understanding karst processes when interpreting stalagmite records. So some stalagmite records go back 500,000 years, and there's hardly any mention of how the karst and the cave could have changed over those 500,000 years. And that seems to me unlikely. You need to understand the site and how the cave is developed in order to understand your stalagmite record. Imagine there's more than a few instances of spikes that have been interpreted as climate in stalagmite records, which are probably just caused to a second entrance opening up or an entrance collapsing and being blocked and then changing the ventilation at a site. Okay, so to move on to the final site where we'll talk a little bit about where all this CO2 come from. So this is Conch Caves in Turks and Caicos Islands. So, this is a Caribbean site. This is a flank margin site. So this is basically that's sea level, basically. So this is my PhD student, Harriet Ridley, who is en route to distribute some CO2 and temperature monitoring equipment within the cave. So we chose something that was well out of the maximum sea level, about a meter higher than maximum sea level to put the equipment. You can see some high water marks here in the back. And what we found was kind of surprising, that the CO2 in the cave was linked to sea level. So the higher the sea level was, sea level is the dashed blue line here, the higher the sea level was, the more carbon dioxide there was in the cave. And I'm not sure anybody had ever seen this before, so I was surprised to see this anyway. Maybe it exists from somewhere else, but I'd never seen this. So this raises the question, where does all this carbon dioxide come from? So the classic model is that the carbon dioxide is produced in the soil and then percolates down through fractures into the cave. Maybe drip water dissolves some of this carbon dioxide and then it comes into the cave and degasses, and that's where the CO2 comes from. But this doesn't really match with our data. If sea level is rising, why would that have any effect on how carbon dioxide is coming down from the soil. So we thought about this a bit. And then we concluded that basically this might have to do with something called ground air. So ground air is CO2 that may not be directly derived from the soil. So water moves particles, organic particles, down through the karst. The karst filters out these organic particles, and then they just sit there waiting to be oxidized by bacteria within the karst. And when that happens, that CO2 just sits there. So there's this idea that, that CO2 could actually be from ground air. And what's happening here is sea level is pushing the CO2 up from ground air into the cave. So this is just a graph showing some sites that probably have ground air as their main CO2 source versus the Earth's atmosphere. And there's a very good continuum between those two. There's two end members, the Earth's atmosphere and ground air. So this is a concept that is really gaining traction, this concept of ground air, over the last few years. So most of these papers are just really from the last 2 years, really. And there's some papers from Dave Matty and Tim Atkinson here. And just to highlight a couple quotes, this is Burgle 2017 GCA, that their data is implying that a subsoil carbon dioxide source is contributing carbon to speleothem, something that we put out in the last month. It's becoming increasingly clear that a substantial reservoir of carbon exists in the unsaturated zone of aquifers. But a lot of these papers are from literally the last 2 or 3 years. But if we go back quite a bit, there's a paper by Tim Atkinson published in 1977 that says that a source of CO2 in the unsaturated zone is proposed to account for this discrepancy in spring geochemistry. So Tim had proposed that there's something like ground air in existence 40 years ago, and it just took the community 40 years to embrace this idea. But really in the last couple of years, we're starting to suggest that it probably does exist. So to conclude, cave microclimate is probably affected by external versus internal temperature differences, but the geometry of caves is also very important. It's critical for stalagmite-based climate records, but also important for understanding the climate cycle. If there is this pervasive reservoir of ground air, and it's in karst, but there's no reason it shouldn't exist outside of karst as well, how much carbon is actually down there? It's intriguing to think of how poorly quantified this reservoir of carbon actually is. Some questions: how does cave development actually affect the cave microenvironment? Again, this is something that's never really talked about in stalagmite paleoclimate papers. And this one seems a little bit out there, but how do cave winds affect stalagmite records? There's been a couple papers recently that suggest that stalagmites are affected by the rate at which air moves over them. And this is something that really is completely ignored and really shouldn't be. So this might represent one of the frontiers in stalagmite paleoclimate research. So I'll conclude with a picture of myself looking rather suspiciously at a early bit of cave monitoring equipment that I inherited from Andy Baker. Thank you very much.